Okay, we've got the section 5.6 notes, rational functions. Objectives at the top. I want to point out specifically that the second one, use arrow notation, is not explicitly stated in here, but we will talk about that. And I'll try to highlight it that same neon green color so that you see it when we go back to it. So to start, a rational function f is, see, typo right off, the quotient of two polynomials. So if we have a rational function f of x, typically we write this as p of x over q of x. It doesn't really matter what we call them. And this is where q of x is not equal to 0. That means that the denominator is not a zero function. So we will talk specifically about what happens to our domain if we are dividing by something, if we are dividing by a 0. We're going to fix that. In the meantime, let's pop over to the left-hand column here and talk about our parent function. If you're not super comfortable with the function, then make a table. And we're going to start with 0. I'm going to stick it in the middle here, which means y would be 1 over 0, which is not okay. We don't ever divide by 0. So what happens with this function is we draw in our vertical asymptote at x equals 0. That dotted line is a reminder that our graph can actually never ever cross that. So I got 1, which is 1 over 1. It gives me a 1. I can stick in 2. I get 1/2. I can stick in 1/2, which gives me 1 over 1/2, 1 divided by 1/2, which gives me a 2. And just so I have a little more, 3, which would be 1 over 3. So when x is 1, y is 1. When x is 2, y is 1/2. When x is 1/2, y is 2. When x is 3, y is 1/3. When x is 4, y is going to be 1/4. And it's going to go the opposite way here. When x is 1/3, y is 3. So this is going to approach the x-axis, and it's going to approach the y-axis this way. I know it's never going to cross the x-axis because there's absolutely nothing that I can divide 1 by that's going to make it equal 0. And then we know from the very first number we plugged in, we can't even use x equals 0. So now I'm going to go the other way. If x is -1, I get 1 over -1, -1. If x is -2, -1/2. So we're going to get the same shape. Here, we'll make it fit. Same curve type over here on the lower left-hand side, quadrant 3. Just a reminder, this is an odd function because it can be rotated around the origin. And if we're looking at that algebraically, it's because if I plug -x in, I get -y. So that works. Okay. I do want to talk about the arrow notation, as long as we have our standard graph here. This is what you're going to see. As x goes to infinity, that is, our x's are heading out this way and getting bigger. Our y, or our f of x, goes to 0. I'm just getting closer and closer to 0. We can do this at the other end of the graph as well. As x goes to negative infinity, f of x is also going to 0. Notice that it is approaching 0 from below. Doesn't really matter, it's still approaching 0. Also want to take a look at what happens at the asymptote. So coming up here, as x approaches 0, and I'm going to use this little superscript, the plus, from the positive side. So our x is approaching, we're going this way. Our f of x is approaching positive infinity. That superscript, that plus, just means I'm approaching 0 from that left-hand side, from the, we could say, positive side. But when we move that asymptote, it could be positive on both sides, it could be negative. The last part we're going to look at down here is as x approaches 0 from the left side, from the negative side, we got f of x approaching negative infinity. And let's see. When I say x is approaching 0 from the left, here is along the x-axis. Let's not erase that. That's saying as my x is getting closer and closer to 0, I want to know what's happening with the y. And that is all arrow notation is telling us. Okay. So back over to example 1 here. We know that x minus 3, let's put that in a different color. Anytime we add or subtract to the x, we are making a horizontal adjustment. So this is a horizontal shift. Three to the right. So that means my whole graph shifts 3 to the right. That also means that my asymptote shifts 3 to the right. So my asymptote is here now at x equals 3. That dotted line means I cannot use 3. So when we talk about the domain, this is the set of all x such that x cannot be 3. That's how we're writing that in set notation. A lot of times what you are asked for in the homework platform is interval notation. And that means I can use everything from negative infinity up to 3. The parenthesis again means I cannot use 3. And then I'm using everything from 3 up to positive infinity. Again, that's everything there except for 3. And then my graph is going to look exactly like it does to the left. From the asymptote, over 1 up 1, over 2 up a half, over 1/2 up 2. Still's not going to cross the x-axis, and it's not going to cross my asymptote. So again, with the arrow notation here, as x approaches 3 from the left, f of x approaches negative infinity, and up at the top, as x approaches 3 from the right, f of x is approaching positive infinity. So we're going to take a look at another example here at the bottom. We want to find the domain first using a graph, then also using the function. Notice here, I have the asymptotes drawn in at x equals -1 and at x equals +2. Okay. That means my domain goes from negative infinity to -1. That's this part of the axis, right? Open circle. When you can't use it, that doesn't look as open as I'd like it to, but let's see if we can stick a, there we go. And then we go from -1 to +2, this part. And then we go from 2 to positive infinity. So it's nice when you have the graph. It is pretty easy to figure out what that domain should look like. Let's see what happens when we use the function. So here's our function, g of x, and this is the function for that graph, so we should end up with the same domain. I'm going to start by factoring. I'm going to factor the numerator. So here I start with x squared. The only way to get x squared is x times x here. The only way to get a 3, because it's prime, is 1 times 3. I want to end up with a positive 2x, which means it's going to be +3 minus 1. If you don't remember how to factor, reach out. We will be factoring quite a bit. I'm going to do the same thing with the denominator. Nice and straightforward. The only way to get this x squared is x times x. The only way to get 2 is 2 times 1, or 1 times 2. This has to be negative in the middle, which means my 2x has got to be negative while my 1x is positive. Notice there is nothing in common in the numerator and denominator, so I cannot cancel anything. But my asymptotes are going to happen wherever I create a 0 in the denominator. So I'm coming down here to my denominator. I know that x minus 2 cannot be 0. I'm going to write it this way. X cannot be 2. That gives the x equals 2 asymptote. Remember, that dotted line tells us what we cannot have happening there. This dotted line means I cannot plug in 2. I'm going to do the same thing over here. X plus 1 cannot be 0. X cannot be negative 1. This gives us our x equal negative 1 asymptote. And if you go back, x cannot be negative 1, x cannot be 2. So in set notation, set of all x such that x cannot be negative 1, x cannot be 2. In interval notation, negative infinity to negative 1, always smallest to largest when we are using interval notation. Negative 1 to 2, 2 to infinity. Everything in the domain except for a hole at negative 1 and a hole at 2.